welcome our next speaker, Chris Freiberger, who is the Fishery Commission's guru as it relates to barriers and sea lamprey control, to talk about barrier threats and opportunities. Chris?
Thank you, John. Good afternoon, everyone. So as John said, we'll be talking about threats and opportunities as it relates to barriers around the basin. And one thing I think all of us know and certainly agree to is that the prerequisite for rehabilitation of the Great Lakes fisheries, a lot of that rests actually on effective sea lamprey control. And not only from a control perspective of the lamprey moving upstream, but also for the fact of reducing the application of TFM upstream in those tributary waters. So sea lamprey control program risk, we heard about a number of them already, both from Bruce and Aaron. Spoke to the loss of social license and lampricide resistance, so I'm not going to spend any additional time on that. But the other risk that we look at from a physical standpoint is barrier failures, and that is either the breakdown of the barriers themselves or the removal of key blocking structures as a result of connectivity in the systems. In the U.S., what ultimately what that means to the program is, in the U.S., if we remove those barriers, if we look at the amount of habitat that's available upstream of our lowermost barriers, we're looking at about a river length about 2 times of which we're treating already. In Canada, it's even much greater than that at 7 times. So it just gives you some perspective on how much habitat is available upstream, how much additional habitat would need to be treated with TFM, and clearly it's not as an effective control method as the barrier themselves. So we look at program risk as it relates to barriers. I'm going to use the word barrier and dam. You'll hear me say that interchangeably. But ultimately is aging infrastructure. Obviously, most of the dams that we rely on for sea lamprey barriers may be 150, 100 years old or 50 years old, so it's old infrastructure. Generally, when we look at a structure, anything over 50 years of age is essentially we're looking at its engineering life expectancy to end at that point in time. There's also high maintenance costs to maintain existing dams, particularly if they're not being used to generate income anymore. So there's a cost associated with insurance liability and just general upkeep. And climate risk, as we see a change in climate with increasing storms and discharges in these river systems, physically it may impact the structures. The other big key issue, which I think most of us or all of us are supportive of, is removal of dams, of barriers. Obviously, we're interested in aquatic connectivity in these systems, ultimately recognizing that if we're going to restore the fisheries of the Great Lakes and river systems, that aquatic connectivity is something that we're trying to achieve. So there's a lot of synergy and energy around removal of structures, which is also often works in cross purposes with sea lamprey barriers. Loss of purpose of dams. Again, many of these dams that we use as what we call de facto barriers that were put in place as a bill or something at some point in time ago, we actually use as barriers and do treatment downstream of those. So ultimately, if these dams are not serving a purpose anymore, the owners often obviously want to remove them for some of the other things I already had mentioned from a liability or financial standpoint. There's also regulatory and financial challenges that Bruce spoke of, and funding availability is when we look at aquatic connectivity and dam removals, there's a lot of funding out there to actually go out and conduct this type of work. Bruce, I'll go through this slide pretty quickly, but Bruce had mentioned this was the Tittabawassee flooding back in 2020. Ultimately, the Edenville and Sanford dams failed, and there were assessments done in the tributaries upstream of that a couple years after, and those 4 tributaries were treated in 23 at a cost of about $661,000. This same storm that happened in May of 20 also had an impact on the Grand River barrier, 6th Street Dam in the city of Grand Rapids on the Grand River. And that dam serves as a sea lamprey, an effective sea lamprey barrier up to about 24,000 CFS. And there's a plot of the USGS gauge here. Anything over the 24,000 CFS, the barrier becomes inundated. It is no longer an effective sea lamprey. It's no longer an effective sea lamprey barrier. We had flows during the same storm, or we had, discharge of about 30,000 CFS. Lamprey were able to get upstream. We found during our assessments a couple years after that 2 of the tributaries had been infested with sea lamprey, and ultimately resulted in a treatment of one of the tributaries in 2023 of a cost of $146,000. So 1, we're looking at a failure of a structure. 2, we're looking at changes in climate. We're looking at changes of discharge and flows into the systems as we have these intense storms. These are just a few that we have records are. I'm sure as we begin to gather more information and document what is happening at these additional other barriers, we're going to find this to be more often the case. So, where are we at? So, over the past 10 years, and I'm going to say specific, more particularly in the last 4 or 5 years, there's been a tremendous work effort on the part of the control agency, DFO, and U.S. Fish and Wildlife Service staff to actually do desktop analysis, to get out and look at the sites of barriers all through the Great Lakes Basin, essentially look at the structural integrity of those structures, to get some idea and some understanding of if they really are effective barriers or not, to understand who the landowners are. A lot of these dams, there was no idea who actually even owned these dams. The state had no record of them. So there's been a tremendous amount of work just hitting the ground, trying to do an assessment to get an inventory, to develop an asset management plan so we can start to try to figure out our way forward here. So through all of these discussions and gathering this information, we really wanted to start looking and trying to understand what we call the lowermost barriers in and around the Great Lakes. And we're defining that it is the first man-made structure that prevents or delays sea lamprey migration upstream. The significance of those lowermost barriers is that they extend the time between lampricide treatments, or they limit the spread of larval infestations. So this is a huge lift, as you can see. Over the last 10 years, the program itself was looking at 7,000, and you heard that right, 7,000 barriers around the Great Lakes Basin that we thought had some level of importance to the program. Through the inventory over this last 10 years, now we're looking at 462 barriers that we've identified that may be critical to this program. So what that means is we can really start to hone in and really understand how important each of these 462 barriers are. We can begin to refine those numbers, better understand what sort of control those barriers do present, and for those other 6,500 dams that we thought were important before, we can actually get out of the way and help support actually, working with partners to get leverage funds to get some of those dams removed, which is just fantastic news. So as we work through this 462 barriers, Lisa Walter in the back of the room here, and many others will be working with the Council of Great Lakes Fishery Agencies, CLC, and individual agencies, basically to roll out these barriers, identify them, and work through those barriers and see what is important to those individual agencies, partners, tribal, First Nations that we're working with. Are there ways that we can look at fish passage, look at fish production, look at sea lamprey production potential, and make sound-based science decisions on how those barriers are going to be managed. So what does this all really mean? Are low-head dams and barriers harmful? Well, what we do know is that they obviously are essential to the sea lamprey program and the management of the Great Lakes fisheries. We also know that we're putting a static structure in a dynamic river system. So we know that it has impacts on river stability. And we need to understand what those long-term changes are by putting these structures in place, or the structures already in place, how that's going to make the river react. And ultimately this comes down to looking at risk management. Can we actually predict what's going to happen to that structure, how that river is going to react, either with an older structure or if we put a new structure in place? And this is a more comprehensive look and the Sea Lamprey program has taken a look at barriers in the past. Largely, it's been in the past of, we've got sea lamprey in the system, we need to get a barrier in place. Where can that barrier be located to deal with the treatment issues? This has taken a much broader look at it, trying to understand and answer those questions as well to be most efficient as we can. But where can we put a structure in place that is going to serve those purposes, but also with that structure that it has the integrity to withstand the river system and all the dynamics within that river system, so it can serve there as long as it can, and we can avoid and minimize impacts on the habitat in those river systems to try to get a better understanding of exactly what these barriers are doing to the river system, and there is a way that we can actually try to minimize it, because we're certainly concerned about the impacts that it has on habitat. So as part of this process, planning process, we talked about prioritization and discussions that will allow for project management, funding, and partnerships. I spoke to that. There's out of this has come some significant funding initiatives, both from the U.S. and Canadian side, to actually address infrastructure concerns that we're looking at. And at this point, looking at our best estimate we have is about $80 million worth of infrastructure needs to be addressed in the barriers that we have throughout the basin. Excuse me. So, to me, what I'm really excited about, and I just started to touch on, is the next item is the geomorphic studies. And what we are going to begin to do, or what we actually have been doing, is looking again, doing a desktop analysis to take a look at the river systems in and around these barriers, looking for instability in these systems, and ultimately, if needed, to get out on the ground and actually conduct geomorphic assessments. We'll be looking at, around the structure itself, upstream and downstream of the impacts of that structure, looking at sediment transport, looking at the habitat that's associated with it, being able to look at change and the rate of change to make predictions on what's going to happen to that barrier. Is there something that we need to address right away or not? And so we can make smart decisions on how we need to address whatever infrastructure needs are there. The next piece of it is doing H&H modeling, is either 1D or 2D modeling. When we collect the geomorphic information, that can be collected and put in these 2D models. And this is going to be paramount to understand on these 462 barriers that we have, when are they actually, based on modeling, when are they actually effective barriers? Is that as a 10-year storm, a 15-year, or a 20-year storm? That's coupled with hydrometric monitoring that we're doing, that we're setting up at certain dam locations here. And when we breach a certain size design storm, we know that the larval assessment crews can get up there and look to see if there has been any escapement. The 2D modeling is more looking at the existing dams that are out there and trying to understand what that means from a fish passage standpoint. When we go in to work on a particular dam or a certain site or certain designs of dams more effective at passing fish, having less impact on sediment transport, if we're going to modify that dam, we then have the information that we can work with engineers to try to achieve fish passage for whatever fish species at that point in time, so trying to gather that information. And then lastly, part of it is looking at the structural, which we've been doing, but looking at the structural integrity of our highest priority barriers. This is just a slide of just going out and collecting some geomorphic information on the landscape. So what started driving this somewhat? This is a case study that we had done on the Clinton River. It's located in southeast Michigan. What you can see on here from the top of the screen is that's the most upstream, and you work downstream, that goes downstream. You can see it goes over the top of a dam structure there. What had happened in the significant watershed changes, land use changes within this watershed, a lot of instability in this river system. It ended up in cut off avulsion upstream of the dam, where now 100% of the flows, if you're looking to your left, the flow goes actually around the dam. So clearly it's not a sea lamprey barrier. Michigan DNR was also concerned about it with steelhead and potentially other salmonids getting upstream into one of the trout streams upstream. So there was an interest on their part as well to get this to serve as a barrier again. So with this cutoff avulsion, there was an engineering firm that was hired to come in, and essentially this is the top end of the avulsion. There was a sheet pile that was driven, and there was some earth that was moved in front of it to block the avulsion, and essentially it addressed the symptom and not the problem. And we got out and started looking at it, and it's like, this really probably isn't going to last very long. You know, if this lasts 5 years, we're going to be lucky. Well, the reality is it lasted 6 months. So about $250,000 worth of work. It ended up and created a new path around into the sheet pile, and we have an avulsion again. So what we ended up and did is, like, we really need to step back. Our program largely has just looked at what's happening around the structure. And if we're really going to resolve this issue, we need to look what's happening in the watershed and upstream of the system, looking at stream stability. So what you see here is the next meander bend upstream. And what's happening is that meander bend, if you look at it over time, I don't have it in this slide, but if you look at it over time, that whole meander bend's getting tighter and tighter, and it's going to actually end up and cut through this meander bend like you see right here. It's going to create a cutoff, just like we saw downstream at the dam. Ultimately, it's going to cut in the next bank, and it's going to actually eat back around the dam into a new rivulet and cause an avulsion. So it's like, if we're really going to address this problem, and this is an important enough barrier, we need to come up with a different option. So ultimately, this is just a conceptual design. We're at a 60% design phase now. But essentially what the blue lines you see in there is a new river channel. The red line in the center is the center line of the channel. Essentially what we're doing, we're using the principles of natural channel design to go in, create the best habitat that's possible, to come up with a stable stream, a dynamically stable stream system, if you will. But we're increasing the slope of that channel through there based on the amount of sediment load that system is receiving. As we increase channel slope, we can move the sediment through that system over the top of the dam. So this is the ultimate design that we're coming up with. We actually just got a construction agreement signed with the company that owns this ground earlier this week. So this is very much a different approach than what we have utilized previously. So here's another example. This may look familiar to many of you in New York. This is the Salmon River Fish Hatchery. This is on Beaver Dam Brook. There's a green barrier here that basically is a weir type structure to move fish up into the hatchery. And working with DFO, with New York DEC and the Commission, trying to identify to get a sea lamprey barrier in place. It'd be a new barrier structure in place that would serve as a sea lamprey barrier, but also would help New York DEC move fish up into that system. So we went out and conducted a geomorphic assessment on this river system, and also collected LiDAR data out there on the site. This is phenomenal LiDAR data. The guy we're using, they're getting about 30,000 points per square meter out here, so it's fantastic LiDAR data that we're getting. Ultimately, I'm just putting a cover overlay on here, but essentially the red area where the red arrow at the top, or line coming down, is where I'm calling it the green barrier is located. But the red area is where essentially where the water is at. And if you look toward the bottom part of this side here, where the red's at, you'll see rivulets coming through there that are fairly small. But we're able to pick all those up. And when you began to look at this geomorphic information and the LiDAR data, it became very evident this is not a great place to put a barrier. We're going to have avulsions around this and cause tremendous amount of instability and downstream degradation. So this was a great example of one project, or these two case studies. One that we're currently working with is at the Clinton River. This one at Beaver Dam Brook, where we're looking at decisions of putting new barriers in. So in conclusion, unstable stream channels worsen ecological problems, and we're seeing that all through the Great Lakes Basin, largely as a result of, again, climate change and land use for sure. And we can be proactive by doing these geomorphic assessments to provide valuable insights for effective decision making. because we're able to predict how quickly some of these changes can happen and that they are going to happen. We can see them if we actually open our eyes, start measuring, and start looking at those. So the benefits for the commission: it ensures uninterrupted sea lamprey blocking, supports sustainable infrastructure projects with long-term success for many, many years when we make that investment. For federal agencies, federal, state agencies, and all our partners. And this also, for the commission, provides data to guide project development and policy improvements, and shifts focus from costly restoration to cost-effective protection. So, thank you.
Thank you, Chris, and again, we'll just keep moving forward.